Kia ora anō. In the last lecture we saw a generic traversal algorithm. To make this generic algorithm specific, we need to specify the rule for choosing the next grey node and the next white node. Different rules will lead to very different results. In this lecture, we study depth-first traversal, more commonly called depth-first search or DFS. The rule here is that the grey node chosen is always the one that has been grey for the shortest length of time. The rule for choosing the next white neighbour is unimportant here, and we'll employ the convention that when there's a choice of white nodes, we'll choose the one with the lowest index. So the distinguishing feature of DFS then is that it takes us away from our chosen route as quickly as possible. Let's look at an example to see what I mean. So here's a digraph. Let's perform a depth-first search on it, starting at the node 0, and we'll employ our convention. When there's a choice of white nodes, we'll grab the one with the lowest index. Okay, so we'll start at 0, we'll colour that grey, we'll choose a grey node, we'll choose an out neighbour, a white out neighbour. We choose one. Now we've got another choice of grey node, and so we choose the one that's been grey for the shortest length of time, so that's the one we just visited. That's 1, and we choose a white out neighbour, choosing 5. Again, we've got a new grey node, so we're going to choose that. We'll go to 2. We'll choose the latest grey node again. We'll go to 4. So as quickly as we can, we've moved right through the graph and away from the route as fast as we can. Now 4 has been grey for the shortest length of time, so we'll choose that. It's got no white out neighbours, so it turns black. We go back to 2. Again, it's got no white out neighbours. It turns black. 5, well, it does have a white out neighbour. That's 6. So now we're going to choose 6. It's the youngest grey node, but it's got no white out neighbours, so it turns black. We backtrack to 5. All its white out neighbours are done. We backtrack to 1. It's got 1 white out neighbour, so we visit 3. Now we grab 3. That's finished, and we're all done. Notice that the choices we were making could be done in constant time, so the running time for a DFS is going to be linear in the order plus the size of the graph, assuming of course that we're using adjacency lists. Now the basic idea of choosing the most recently visited grey node is captured by the last in first out protocol, which in turn is seen in the stack data structure. Thus, if we store grey nodes in a stack as we visit them, we can get the exact behaviour we want. Let's then look at the pseudocode for DFS. So here's the code for DFS search. Again, we split it up into 2 routines. Here's DFS, which is the equivalent of what we called traverse before, and here's DFS visit, which is what we simply called visit before. DFS again takes a graph G. Here we've got a bit more set up this time. We set up a stack S. We set up the colour and predecessor array as before, but we also set up these new arrays seen and done, and they'll record the times of events as we go through the algorithm. So here we're just initializing the colour array and the predecessor array, and we've got this new variable time which we start at 0. So as before, we'll iterate through each of the nodes. We'll look for a white node. When we find a white node, we'll pass it to DFS visit, and we'll dive into here. So what happens in DFS visit? Well, we pass the node S, we'll visit the node, we'll color it grey. The predecessor array was already set to be null everywhere, so we don't need to set the predecessor. We'll say that a node was seen at the time it was first visited, so that's the time a node turns grey, is the seen time. So we'll set that to time and we'll increment the time. And then we'll we'll push S into the stack, and then we'll enter this main loop, right? And within this main loop, we'll be saying, well, the stack is not empty, so while there are some grey nodes, then we'll peek into the stack, so we'll look at the node that's on the top, and so that's the most recently visited grey node. We'll look for any white neighbours. If it does have a white neighbour, we'll visit those neighbours, so we'll visit the neighbour V, we'll turn it grey, we'll set its predecessor to be U because we cross the arc UV to get there. We'll set the scene time for V to be the time we're at now, and we'll increment time. All right, so notice that every time a node changes color, we'll record its time and we'll increment time immediately after. And then we'll push V onto the stack, and we're back to the start of the loop, where we'll look at the thing that's at the top of the stack, the node that's at the top of the stack, and try visiting its neighbours. If the node at the top of the stack doesn't have any white neighbours, then we're in this situation down here. We'll remove that node from the stack. We'll colour that node black. We'll record the time that we did that, so that'll be in the done time, and we'll increment time, and then we're done. We'll be back up to the loop, and so long as there are some grey nodes, so the stack is not empty, we'll stay in this loop. Once we're done in this loop, we'll return to our main algorithm, DFS. We'll see if there's any white nodes. If there are no white nodes, we'll simply return the predecessor array, so that'll be the search forest, and we'll return the seen and done times, which will be useful for any analysis we want to do. So notice the differences from the general traverse algorithm. All we've done here is we've added in the stack, we've added in the seen and done arrays, we've kept track of the time, and that's pretty much it. We can write DFS visit in a recursive fashion, that is, in a way that calls itself. So that's not very surprising, as recursion mimics stack behavior. Indeed, calls to subroutines are stored in the call stack that we often simply refer to as the stack. So let's have a look at the recursive version of DFS and see how it differs from this one. So the first couple of lines remain the same. We colour the node we're past grey, we record the scene time, and we increment the time. But we don't need a stack here, so we'll change what's below here. Okay, so we've got rid of the stack, and rather than expressing this as a while loop, let's call it a for loop instead, and we'll just loop through each neighbour of our given node S. So for each out neighbour V of S, we'll see whether that out neighbour is white. So if V is white, then we won't colour it grey immediately. We'll simply keep the tree up to date. We'll record the predecessor of V to be S, and then we'll dive down into another call to DFS visit. So we can get rid of all of this and simply make another call to recursive DFS visit. And there we'll colour it grey, update the time variable, and so on. Now, if once we've visited all the out neighbours, we haven't found any more white ones, then we're down here. So here we colour the node black. This should be a S. We'll record its done time again S, and we'll increment the time. And I guess we need to set up the indentation, move the indentation across so this all lines up down there. So it's very much the same algorithm, it's just expressed in a recursive manner rather than using the while loop we had before. Let's then go through a detailed example and see how the time and seen and done variables work, and then we'll look at determining whether arcs are tree arcs, forward arcs, back arcs or cross arcs by using the seen and done timestamps. Okay, so let's go through DFS visit, the recursive version, on this small digraph here, and we'll start our traversal at node 0. So you can see here I've set up the array seen, the array done, the predecessor array. I won't initialize it with nulls everywhere just to make it easier to write in. We've got our time variable here, so let's start. So what do? We color everything white. We choose S to be node 0, and then we call DFS visit. What's the first thing we do? We color S grey, so we color 0 grey. We set the seen time to be the current time, which we should have set to 0 at the start. So the seen time is 0. Then we increment time, so we're at time 1. Now we loop through each of the out neighbours of 0 and check whether they're white. So the first out neighbour is 2. Is 2 white? Yes, it is. So we set the predecessor of 2 to be 0. So predecessor of 2 to be 0. And we should have set the predecessor of 0 as -1, which we would have done in our initialization. And then we call recursive DFS visit with 2. So we already had one recurse DFS visit with 0. Here we are calling DFS visit with 2. We'll color 2 grey. We'll set the seen time of 2 to be 1, the current time. We'll increment time, and then we'll start visiting any neighbours of node 2. Has it got any out neighbours? Yes, it's got one out neighbour, and that out neighbour is white. So we set the predecessor of 4 to be 2. So predecessor of 4 is 2. And then we call recursive DFS visit with 4. So what do? We colour 4 grey, seen time to be 2. We increment time, and then we check for any out neighbours of 4. 4 has no adjacent nodes, so we colour this thing black. We colour it black. We set the done time of 4 to be the current time, which is 3, and we increment the time. So we're done with that call. We pop back up in the stack to 2, so we're back at 2. We say, we carry on looking for 2's out neighbours. Okay, it doesn't have any more out neighbours, so we set the colour of 2 to be black. We record the done time of 2 to be 4, and we increment time. We're done with that call, and again, 0 has no more out neighbours, so what are we going to do? We're going to colour that black. We're going to set the done time for 0 to be 5, and we're going to increment time. And we're done there. Okay, let's just make a little bit of space here. We'll be back up in the main DFS routine that I had over here before. We'll choose a new white node. We'll choose 1. It's the one with the lowest index. That's the convention we use. So we choose 1. What will we do? Dive in to recursive DFS visit with 1. Okay, so we're going to colour 1 grey. We're going to set the scene time of 1 to be the current time, and we're going to increment time, and then we're going to start visiting each out neighbour of 1. 1 has a couple of out neighbours, 0 and 3. We choose 0 first. We see that it's not white, so we do nothing. We choose 3 next. Is that white? Yes, it is. So we set the predecessor of 3 to be 1. Set the predecessor of 3 to be 1. And then we'll dive into DFS visit with 3. So we'll colour 3 grey. We'll set the scene time to be the current time. The scene time of 3 is 7. We'll increment time, and then we'll look for any white out neighbours. 2 and 1 are the only white neighbour. Only out neighbours of 3. Neither of them are white. So we into this situation, we'll colour 3 black. Record the current time as the done time for 3. So the done time for 3 is 8. And we'll increment time. And we're done with this call. So we're back up here. There's no more white out neighbours of 1. So we'll colour 1 black. We'll record its time. We'll increment time. And we're all done. The only thing I've missed out is I forgot that we didn't record the predecessor of 1, which was null. So at this point, we'll jump back up into the main DFS algorithm, and we'll return the scene, done, and predecessor arrays. We'll have a look at what we can do with these arrays. So as before, we can, we can think about the search forest we had here. We can look at which arcs we crossed, and so we'll colour the arcs we crossed blue. So the blue arcs are tree arcs. The arc from 0 to 4, well, that'll be a forward arc because it's going down the tree. These two will be cross arcs because they're between different trees in the search forest. And this arc, 3, 1, will be a back arc because 3 is a descendant of 1 in this search tree. So let's now look at a result that tells us about the seen and done timestamps. We'll suppose that we have run a depth first search on the digraph G, and we'll call the resulting search forest F. So we'll let V and W be nodes in G, and we'll suppose that we saw V before we saw W. During our traversal, we visited V before we visited W. So there are two cases. Either V is an ancestor of W and F, or V is not an ancestor of W and F. We'll look at the first. And so we've got this result. If V is an ancestor of W and F, then we saw V first, then we saw W next, then we were done with W before we were done with V. And that's based on the assumption that we saw V before we saw W. Okay, the first bit is assumed that we saw V before we saw W, but this is a stronger statement, right? We saw V, we saw W, we finished with W, and then we went on to finish with V. Why is that? Well, think of the recursive form of the algorithm. After visiting V, we are going to explore all its neighbours and its neighbours' neighbours, and so on until we eventually visit W. We'll continue to visit all the neighbours of W, descending into the recursive DFS visit until eventually we return back up the stack and we're done with W and finish up the stack when we're done with V, and hence our result. Similarly, there's another statement. So if V is not an ancestor of W and F, then we have, so the statement here is that we'll be seen and done with V before we see W, and then obviously done with W will come last. Again, that statement should be fairly obvious from the recursive nature. We explore the subtree below V completely before turning everything black. So we'll see V, we'll explore everything below it, we'll return back up the stack, we'll be done with V, before we head off to a part of the tree that has W in it, we see W, sorry, and then we finish with W, hence our result. This result tells us that not all timestamps are possible. So it's not possible to have seen V, then seen W, then be done with the V before we're done with W. And again, just think of the recursive nature of it, wouldn't allow this setup. So we'll put a line through that because that's not possible. How is that useful then for helping us to classify the arcs in the digraph once we've got a search forest? Well, we can simply look at the seen and done timestamps and use our previous result to do so. So suppose we've got the arc VW, we've run a depth first search and got the search forest F. Then if VW is a forward arc or a tree arc, that means V is an ancestor of W in the search tree. In that case, we're in the first case of the previous result, so that means VW is a tree arc or a forward arc if and only if we're in the situation where we saw V, then saw W, we're done with V, and then, done with W, then done with V. So that means VW is a tree arc or a forward arc if and only if we're in the situation we saw before where we see V first, then see W, we're done with W, then we're done with V. So that's exactly the first case of the previous result that we had. And it's only when V is an ancestor of W within F that VW is a tree or a forward arc. Let's check that result in our example over here. 0, 4 was a forward arc. We saw 0 at time 0. We saw 4 at time 2. So seen 0 is less than seen 4. We were done with 4 at time 3. So second inequality follows, and the last inequality is when we were done with 0, which was indeed at time 5. And similarly, we can make an argument about VW being a back arc when V is in the subtree that we explored after first visiting W. So the argument here is very similar. It's just that we've reversed V and W. And then we're using the same first part from the previous result that we saw. Lastly, how do we tell if VW is a cross arc? Well, we're only going to get a cross arc when we see and are done with W before we even visit V. So in this case, our arc from V to W has no chance of being crossed because we've finished with W before we even see V. Okay, so let's have a look at our example here. We saw that 3, 1 was a back arc, so this would be W and this would be V. And so seen of W is less than seen of V, which is less than done of V, which is less than done of W. So that checks out there. How about in the cross arc situation? Well, 3, 2 is a cross arc. This would be V and this would be W. And we saw and were done with W before we saw and were done with V. So one thing to think about is how can we classify edges actually during the runtime of our DFS traversal? That is, the first time we cross an arc VW, how do we decide whether it's a tree, forward, back or cross arc? I'll leave you to think about that.